Uh, Thank you everyone for joining. So, how many of you know me? How many of you know Bangladesh? Two, three, few people. Yeah. So my background is I'm original from Bangladesh, and Bangladesh is a very small country, which is essentially the size of Nebraska. And I say small. Nebraska is not small compared to population, but if you look at the difference between Nebraska and or US versus Bangladesh, Bangladesh is 66 times smaller than US in like size, but it has almost half the population of US. So that's very highly densely populated country. So we have a lot of water need, like not enough water for people, also not enough clean water for people. That's more of a major issue, and that's what drove me to move from chemical engineering in bachelor's to master's and PhD in environmental engineering. So I did my bachelor's in chemical engineering in Bangladesh, and then I moved to University of South Carolina to do my master's, then PhD in Austin. Then I was a faculty member in University at Buffalo in New York, and my wife was a faculty member in University of Florida. So there were some long distance, and now both of us are in UNL and UNMC together. So 15 years, 6 states. Probably this is the last one, or at least for some time. Yeah, so, and this is my lab group, obviously not. So we have several pets. One of them is actually sick today, so I had to bring her to the vet, and she's undergoing treatment. But yeah, we do fostering, and but this is actually my group who mainly do the work, and we are driving the research grant writing process or idea generation, but students are who or postdocs who do the work mostly in the lab. So two of my PhD students graduated. Dr. Arvind Masood is who started work on PFAS, and I will talk about that. And then now students, all my PhD students are working on PFAS pollution problem. Most of this project, but I also had a lot of undergrads and master students back in Buffalo who really contributed a lot of the work to a lot of these works. So, and we have been fortunate to have a lot of collaborators from Buffalo and then all over US, honestly, like many people from many different places, and funding from different agencies, and also from Doherty Water for Food Global Institute. Thanks to them. So, how many of you watched the movie Dark Waters? Nobody else? What?
It's a good movie.
It's a great movie. It's a great movie. It's a must-watch movie. So, basically, this movie was from 2019, and you can see the cast. The cast is really amazing. Mark Ruffalo and this essentially talks about a lawyer, Paul Bilott, portrayed by Mark Ruffalo. This was actually, and I'm going to the controversial part because this is about DuPont and 3M, how they manufactured PFAS, and they knew about the toxicity of PFAS, but they didn't like disclose it to the public and didn't do anything about it. And they kept dumping waste contaminated with PFAS, and I will talk about PFAS more. But this is the true story that really discovered PFAS and how much toxic they are, what they are causing to humans. This is the actual story of that lawyer. So Bob Willard essentially was a lawyer for chemical companies first, and then he turned around and he discovered this whole issue of PFAS, and this is about based on in West Virginia. So there was a chemical dump. So DuPont was dumping waste near a farmland in West Virginia, and then the farmer lost 193 or 94 cows. Basically, all of his cows died from this, and eventually he and his wife both got cancer from PFAS contamination. Okay, so that's how like it started, and here, and because it's against DuPont, 3M, big companies, probably that's why people don't really know about this movie. Although this is like really Oscar-winning performance here, like it's like one of the best movies I have ever seen, and so it was only open in Netflix from May 1st last year to around October, and no other like free subscription to this movie. But it's only $5 in Amazon. I hate watch it. So basically, what is PFAS? Now we are talking about PFAS. PFAS goes as par, like if we look at the terminology, par and polyfluoroalkyl substances. What it means is essentially, if you look at this structure, so this is the compound that this movie talks about. Okay. So if you look at this compound, chemical compound, carbon and fluorine, together, if you think about organic chemistry, carbon and hydrogen, we talk about alkane, alkene, alkyne. So if we remove in 1940s, what chemists identified in DuPont and 3M, that if we remove hydrogen and put fluorine in there, we can make really strong bonds because carbon is mostly electropositive and fluorine is one of the highest electronegative atom. So if we put them together, they build one of the strongest bond possible. Okay, and that's why it's not naturally possible. There is no natural compound that has carbon and fluorine bond in it. Okay, so this is totally synthetic, and this was called PFOA or PFOA because it has a carboxyl hydroxyl, sorry, octanoic acid carboxyl group here at the end of it, and it's 8 carbon chain. So all of these hydrogens are replaced by each. So this is called perfluorooctanoic acid. Okay, so this is just one of theoretically, like we can have a lot of different PFAS, like more than 10,000 different PFAS compounds, because you can have different carbon chain length, different branching, how many fluorine you can have. You can have different types of functional groups at the end, or have functional groups inside 2 carbon chains in 2 sides. So you can have different configurations. So you can really get a lot of different compounds. So why was it discovered? It was discovered actually to coat surfaces. Okay, so during World War II, when they took the tanks and these companies were trying to make coating for tanks so that the steel tanks don't get corroded, or iron tanks don't get corroded in water. So that was the initial purpose. And then they realized we can put the same thing on non-sticky cooking pans. Okay, so if you look at, if you don't want to watch that movie, there is a 20-minute skit from John Oliver on this. Mind about the language in this. And John Oliver is not always age appropriate for everyone. So say this, but what I'm trying to say is like, then when PM and DuPont saw that this coating can repel water really well, they are fire resistant because carbon fluorine bond is very, very strong. So they are not breaking at high temperature too. So they started putting it as Teflon for water repellent non-sticky cooking pans because they are not degrading at high temperature. So that's when we got non-sticky cooking pan paint, anything and everything where we need water repellency, fire retardant, or fireproofing, they have put PFAS there, which means almost everything is coated with. But some has more than others, right? Consumer products. Like if we think about, we talk about ban plastic and use paper cups. How do paper cups become hydrophobic or water repellent? We put PFAS coating on them. Okay, so it's not always good to think about replacements if we are not sure what will be more important. So, which is we had like all the firefighting foam in fire extinguisher, the foam before they had PFAS in it because they can take out fire. So firefighting foam was developed using PFAS. So that created a lot of pollution around Department of Defense, like Army, Navy bases, or around fire stations, where they are testing a lot of explosions and fire extinguishing practices they are doing. So they have a lot of high concentration accumulation of PFAS around those areas. So we use them in consumer products. We use them in many different applications. We actually use them in pesticides too. PFAS is a surfactant because it has a long hydrophobic chain, and on the other side, it has a polar group, functional group. So this is essentially a surfactant that you can use in different applications. So in many cases, when they develop insecticides or pesticides to deliver in water efficiently, mix them homogeneously in water, they use PFAS in some cases. Okay, so it's really, the point is that we use it in so many ways that they are getting released in the environment. The issue with this is that PFAS has been in the environment for many years, but we didn't have the technical capability or analytical instrumentation before early 2000 or like late 2000 that we could detect these chemicals because they get released in very small quantity that we cannot detect. For example, like in nitrate, we can detect nitrate at low cost because, and if you think about nitrate contamination, we think about a milligram per liter concentration, which is very high. But when we talk about PFAS concentration or other emerging contaminants like this, pharmaceutical pesticide, they are in very low concentration, which is like microgram per liter or nanogram per liter concentration. So, and detecting them at that concentration is very difficult with conventional analytical instruments. So we need high resolution instruments, liquid chromatography, mass spectroscopy, water center, like Dan has developed process methods to identify them in many different environmental systems. So that's how we came to know about them. Okay, slowly over time, last 20 years, there has been a lot of identification of different types of PFAS. And then we started to realize that these, when humans are getting exposed to them, because these compounds are getting in our water, getting in our food, and we are drinking them or eating, they're getting inside our body, they accumulate because these are carbon-based chains. They are hydrophobic, so they don't want to stay in water, and they accumulate inside body or different organs and tissue. Over time, they partition into lipid. So over time, they accumulate and they have several chronic effects. Carcinogenic effect like reproductive hormones get imbalanced, endocrine disruption happens. Then we have different types of developmental issues in children too. There are thyroid cancer, several types of cancer can happen with PFAS. And we call them forever chemicals. Why? Because these chemicals, because this carbon-fluorine bond is so strong, they don't get degraded in natural processes. So typically, if a toxic chemical goes out and if they are biodegradable by bacteria or other organisms, then we don't really think about their toxic effect that much if they're not released in high concentration. These chemicals are going out in low concentration, but they will persist in the environment forever, kind of like they have a half-life of 1,000 years, which means it takes a long time for them to degrade, even if they degrade. Okay. So the other problem is, so there is in water. So if you look at this thing picture, so because PFAS is everywhere, so we get a lot of PFAS in our wastewater from our municipal consumption. Okay, so they go our wastewater in the municipal wastewater, and in the municipal wastewater or drinking water treatment system, the problem is we don't have the technology. The technologies that we use for water treatment now are not really capable of taking out these chemicals efficiently. So that's one problem. So what happens from wastewater treatment plant? Some of them go into the surface water. Then many of the PFAS actually goes in wastewater treatment plant. We get a solid part 2 from the wastewater treatment process, which is called biosolid. And a large part of this goes into biosolid. Not only PFAS, there are other contaminants too, which go into biosolids. And these biosolids get used as fertilizers because these biosolids are very rich in nutrients, okay, like nitrogen, phosphorus. And we use, in Nebraska, 95% of biosolids that are produced is in our wastewater treatment plants, like Omaha or Lincoln wastewater treatment plants, are used by farmers in the state. And this is not only the case of Nebraska, it happens in many different states too. So they are entering our farmlands, they are going into our groundwater, they are in air emissions too, they get back to our drinking water systems. So they are essentially everywhere. Okay. So EPA came out with this regulation last year to stop drinking exposure of PFAS through drinking water. So they said there are almost like 15,000 different types of PFAS, and we don't know which company is using. But they identified like this PFOA, 5 of them individually, 5 specific PFAS individually, that they should have a certain limit that we can allow, which is like if you look at MCL, maximum concentration level here. So MCL is like we need 4 parts per trillion. We can only allow 4 parts per trillion of PFOA in water, which is very, 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 very small. Very, 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 very small. Okay, so it's so small, it's difficult to detect even at that level. But more importantly, if you look at here, that final maximum concentration MCLG, G means goal. The eventual goal for these compounds are 0. What does it mean? There is no safe level of these PFASs in our body. That's what it means. So in our water, there should not be any, like these PFOA and PFOS, at least them. The other ones have some sort of, but they're also so small, you can only, like, they're almost close to 0. So the idea is that PFAS is the new lead. Lead doesn't have any like concentration, a safe limit for exposure. Okay. So the problem is that for drinking water treatment plants, if they have to upgrade their systems, if they have to employ new treatment technologies to take out PFAS from water that they are treating to give us clean drinking water, the estimated cost across the country will be more than $200 million to $1 trillion capital cost. Okay. I just saw a news yesterday that a city in Florida is trying to install one setup for their taking out PFAS, and it will cost them more than $350 million. So, like, I don't know the size of the city. It's not one of those well-known cities. It's not West Palm Beach. Okay, so, but this is the thing. The other side is like they're going into our food sources too. They're going into our soil. They're going into food products. They're going into our milk, beef, everywhere. So state of Maine already banned biosolid application in soil to protect them for PFAS, like from PFAS, because several farmers there did suicide after they lost crops, they lost cattle, they did suicide. So they are really taking it seriously. For milk, there are studies that shows that 1 in 10 cartons of milk that you can buy in grocery store has detectable level of PFAS in them. If you take organic milk, they have 3 in 10 cartons that have detectable level of PFAS. So I don't know if it's organic is good or bad, but that's just an estimation like that came out. This is another story that came out in New York Times in August 31st. Last year, the New York Times is doing a series that says like something is poisoning America's land. And so this is a story, like this is one example from there. In Texas, in a ranch, they found a calf that was stillborn, and they found the PFAS amount in its liver to be 600,000 parts per trillion. 600,000 parts per trillion, right? If we go back, this is our allowable limit, 4 parts per trillion. Okay, so you can imagine like how much. And now they are trying to investigate where the PFAS is coming from. Probably there was some disposal site, either PFAS contaminated waste or PFAS directly disposed somewhere nearby, and the cattle probably drank water that was contaminated by PFAS, something like that. But they're investigators. Okay, so we need to solve this problem. I'll come to talk about that. But how many of you know about nanotechnology? Some of you. Okay. How many of you use nanotechnology? You only?
So you also, right? Two.
No, everyone. Because nanotechnology is what makes electronics possible. Okay. So from this generation of computers, who saw these computers? Oh, yes. Okay. I didn't see them. Who saw this? Nobody? Okay. First generation, obviously. I am from this generation, right? This generation onwards. Like, and we see now all these smart electronics, right? So in our time, it was telephone means telephone, TV means TV, radio means radio. Now it's everything in all together. So how is that possible? This is possible by this. So electronics, so electrical to electronics, that transformation happened in 1947 when we developed the first transistor. Transistor is we talk about chip. Even within the chip, the main component that makes a chip possible is the transistor. Okay. So if you think about transistor, the first transistor was that big, and our iPhone 16 has 16 billion of those transistors inside that iPhone. Okay. So you can imagine that when we went from that size, it has to be very, very tiny atomic scale size of materials that we are producing and using inside phones or any smart electronics. Okay, so that's what we are saying, 3 nanometer process nodes, and I'll explain what that means. But we are using them atomic scale or molecular scale materials. We are making solid materials that are capable of doing much more things than large scale materials. Okay. And we are applying them in electronics, we are applying them in many different applications, in water purification, biomedical application. The COVID vaccine that was made, it was possible because we could make polymer-based nanoparticles that could encapsulate the mRNA from the virus. Okay, so lipid nanoparticle technology, which was discovered, obviously funded by NSF at that time, but yeah, so COVID vaccine is a real case scenario where we were literally saved by nanotechnology. Okay. So if I look at the scale perspective, so if you think about a tennis ball that is 10 to the power minus 1 meter, and if we go down in the scale, if we go like smaller than bacteria, the bacteria is 1 micrometer or 10 to the power minus 6 meter, right? We go smaller than that, viruses, and then we go to the water molecule 10 to the power minus 10 meter around that scale. So in between that, from the nanotechnology is about 1 nanometer to 100 nanometer. So if we go into that scale, if we try to understand again the scale, that from the earth, if you want to find a soccer ball standing on the top of the earth, and if you try to find a nanoparticle standing on top of a soccer ball, that's the same ratio. Okay. So obviously we cannot see them in our naked eye or even with optical microscope. So the thing is that when we go into that scale, we can take the same materials that we use in macro scale, we can design different type of material. So for example, we can have carbon-based material like fullerene, which is called zero-dimensional carbon nanotube graphene. All these can be made from graphite. We know about graphite, right? Pencil lead. Okay, but all these nanoscale material can be made from graphite. I'll come back to this, but the definition of nanomaterials or nanotechnology exists at that scale. So nanotechnology means material manipulation at nanoscale, the scale we are talking about, 1 to 100 nanometer. The nanomaterial definition, first part is, if we take a material, if it's one dimension, either the width or the height or the length, if one of them are within, at least one of them are within 1 to 100 nanometer, we call them nanomaterial. But the definition doesn't stop there. There is another part of the definition. And that part is nanoscale properties have to be remarkably different than its bulk properties. Okay, I'll go back to the previous slide later. The reason I'm saying it, if you think about gold is valuable because it doesn't degrade, right? It's inert. It's used as currency because of that. It doesn't react with anything, but honestly, it doesn't have any purpose. It's not doing any functional work in a sense. Yes, you can put it in as a restoration, dental restoration. There is a lot of gold-plated restoration goes on, and it's really good as a restoration if you put it in the backside or front side. It doesn't matter, but it's a good thing because they don't react with anything. But when we go into nanoscale, okay, if you see these nanorods, nanoshells, nanocages, you can design different structures and you can vary their aspect ratio. Aspect ratio means their length compared to width. You can change them longer. You can change the ratio. You can put them on a different particle and use the shell thickness, change the shell thickness. What happens in that case? We can get different colors, right? What that means, they are interacting with lights a different way. That means they will be differently reactive with their shell thickness, with their aspect ratio, their length, size, shape, diameter. All these things will influence their properties. So we can use them for different application. We can use nanogold as catalyst in reactions. We can use them for biomedical therapies too, for laser-induced cancer therapeutics. We can use them for identifying tumor, and you can use gold nanoparticles too inside the body. So if you inject body with like vaccines, you inject a certain contrasting agent and do MRI scan or PET scan, you can find where the cancer plus tumor is because the nanoparticle will go there and give signals. You can see that. Okay, this is what you can do. The thing is that we can take any type of elements in the periodic table, we can take any type of compound, and we can make particles out of it. The main difference between molecules versus nanomaterials is that nanomaterials are solid. So think about sugar versus sand. Sugar, we put in water, they dissolve. When they go dissolved, they're in molecular form. There is no solid form. But if you take sand, if you put it in water, even if you crush them in nanoscale, they will still be solid. That's not molecular form. Okay, that's the difference. So one is solution, one is a mixture still. So nanoparticles versus molecules, typical molecules are a little bit different. Now, what do? We use the concept of something called nanohybrid. Okay, nanohybrid means if we take different types of nanomaterials, like this is called graphene, which is a carbon-based nanomaterial, and you can put metal nanoparticles on it. So graphene or carbon, like they can absorb contaminants on the surface, and metal nanoparticles can do reactions. So we can combine the properties of two or more different nanomaterials together to improve applications or improve some efficiencies. I'll give more example, but this is a concept that we use. We combine two or more materials, like we can combine carbon-carbon, we can combine carbon-metal, we can combine metal-metal nanoparticles too, and improve their properties for different applications, or see how we can use that for water treatment. So this is what we do in our lab. We design different types of nanomaterials. We look at their properties. If they have a certain chemical property, reactive property, can we use them for water treatment? But at the same time, the other side we see, we are not going to talk about that much. The other thing we try to see if these nanomaterials are also safe, because we can design a treatment technology, but we don't want to end up with a situation like PFAS, that we are designing a nanomaterial to solve an environmental problem, but that nanomaterial itself becomes a problem for us. Okay, so we also try to understand their toxicity, okay. So PFAS we learned nanomaterials. Now we are going back why we need nanomaterials or nanotechnology for PFAS treatment. Okay, so this is a summary of the current technologies that are being developed and current technologies that are there for taking out PFAS from water. PFAS is a molecule, and there are different types of molecules of PFAS in water. So there are different ways you can take them out. There are two things to do. One is you can separate them from water, like we do filtration, right? Typically, we understand filtration, like we take contaminants out from water. That is the separation part. The other part is that this carbon-fluorine bond, that's the major thing about PFAS, like that's what causes the toxicity too. So if we can break the carbon-fluorine bond of PFAS, then we need to do destruction to be able to do that. Otherwise, once we separate the PFAS out from water, we have another problem. What do we do with this all PFAS? Does that make sense? Okay, so there are two questions. One is separation, one is destruction. So if you look at these different technologies, like granular activated carbon is emerging. I don't know why they call it emerging, but if you look at it, emerging technology, mature technology, and inefficient technology. So if we look at granular activated carbon, that is the cheapest option that you can take to separate PFAS out from water. And that's what many of the utilities are doing now. They are just creating huge GAC, like granular activated carbon. These are carbon which are very cheap. You know, Brita filter, we use Brita filter. What goes in is essentially granular activated carbon or powder activated carbon. These are char-based material, like carbon-based material that can take out a lot of hydrophobic compound from water, different types of compounds. So that is an emerging technology. This is very cheap, low cost, but this is moderate efficiency. Ion exchange resin is something also. So these are mostly, if you look at this side, reverse osmosis nanofiltration membrane. You know about reverse osmosis membrane? Right? You heard about it. Many of us use at home reverse osmosis membrane. They actually can take out any PFAS. They can take out any molecule. They are very, very small membranes, filtration devices. So, but they have high energy cost. Okay. So there is a balance we need to do. The other side of it, they are not solving the problem of PFAS degradation. Okay, they are just separating these molecules, but then we are coming up with thermal technology, which is something emerging, but still inefficient in the point that they are highly expensive. Okay, so you have to basically heat them up at high temperature. In many cases, what people do is just take PFAS based solvents or PFAS contaminated solution and then incinerate it, or PFAS containing waste, they incinerate. That is probably one of the most common ways. So we have to come up with like many different technologies people are trying: electrochemical technology, plasma technology, and photocatalytic technology. These are new technologies for destruction that people are trying to do. One other thing is that if you look at here, if we could do biological treatment, microbes could break them, that would be really, really fantastic, honestly, because that would be the cheapest way. Biological treatment processes are very cheap, and we could, if we could use them, that would be fantastic, but that is very, very inefficient. And that's why we have the PFAS problem. So what we are doing now, in case of our lab, we are taking something called graphene iron nanohydrate, so nanocomposite, where we have this graphene, which is one layer of graphite, carbon layer. Okay, the difference between graphite versus graphene is graphite, you know, pencil lead. Pencil lead is non-conductive. If you, they don't pass electron through it, very low conductivity. But if you go into singular carbon sheet level, one atomic length graphene sheets, they will transfer electrons fast. Okay, why? I can explain, but probably we don't have time. But the main difference is when we go into nanoscale, we can see that electrical conductivity. And iron nanoparticle we are using because they can help in driving a reaction called advanced oxidation process in this case, which is basically if you take hydrogen peroxide, this hydrogen peroxide, when in contact of iron, they can produce hydroxyl radical. These radicals, free radicals, hydroxyl radicals, are very, very reactive with different organic contaminants. So we wanted to see if we combine this graphene with iron, will that improve the absorption first, if they can absorb PFAS on surface. Second, if they can degrade PFAS from water. Okay, so that's what we try to do. So these are the examples. So if you see here, there is iron on the left side, graphene, and then this is this graphene iron composite. So this is the graphene sheet. Okay, they don't look like the schematic that I showed, but these are just the planes. You cannot see the individual atoms there. And these are iron particles on top. And then we also tested with two different classes of 4 different PFAS. 2 are short chain, 2 are long chain. Short chains are defined anything has carbon less than 6. Okay, and these are 8 carbon chain PFOA and PFOS. So what we did is basically we put them with the nanomaterial. We shake them with the nanomaterial. So we put PFAS contaminated dosed water and then put nanomaterials with them. We shake them for some time. And after that, we take the supernatant out and centrifuge them and look at how much PFAS is remaining after we did this treatment with nanomaterial. Got it? Okay. So we do the analysis here. So what we found is that there is a lot of graph, okay, go one by one. If we just look at short chain versus long chain PFAS, it doesn't matter which type of material there is, if it's graphene or iron or graphene iron hybrid, it doesn't matter. Most of the performance for long chain is better than short chain. They perform because there is more long chain are more hydrophobic. So these values, log KOW values, are indication of high hydrophobicity. So the more the values, if we know that they are more hydrophobic and long chains are more hydrophobic, they are getting on the surfaces of the solid particles, either that be carbon or graphene or iron or the hybrid, and then short chain are not removed as much. Between these materials, if you look at here, so the gray ones are graphene, red ones are iron, and then green ones are the composite or hybrid. We combine them both. So the green ones are performing quite a bit. And when we have these nanohybrids with hydrogen peroxide, which creates the reactivity, that's when we see the most removal, highest removal of this nanohybrid with hydrogen peroxide. Okay, if we see the kinetics too, the kinetics of removal of this PFAS, so the nanohybrid itself removes about 50% of PFAS in 5 minutes with in the concentration range we were testing. And then if we have nanohybrid with the hydrogen peroxide, then we can get more like 90% removal of the PFAS, which is good. When we say PFAS removal, we are only seeing the decrease of PFAS concentration. So if it's only PFOA on PFOS, we are seeing the decrease. We were not sure if they are degrading or not. So we need to do another type of analysis, which is called high resolution mass spec. Okay, and I have a colleague in University of Buffalo, Dr. Dianaga. Our group specializes on analytical chemistry, and they helped us to figure out what is happening with the molecules. Okay, and what we found is that first, what we saw multiple short chain PFAS. If you look at there on the PF HX like 6 carbon, 7 carbon, and 4 carbon chain PFAS, we find that are breaking from 8 carbon chain. So this is a result of only PFOA and PFOS. And what we see, an interesting thing we find is that the 6 or 7 carbon chain PFAS are producing a PFAS iron complex. Okay, so these two PFAS iron complex they produce. So this is partial transformation. We are not seeing total degradation of the PFAS itself, but we see that with the hydrogen peroxide versus, so with hydrogen peroxide we get more PFAS degradation or more byproduct formation from PFAS compared to when we don't have any hydrogen peroxide there. So when we are not doing just degradation, when we are doing adsorption, we see some less. So in the next project, what we did, so that was first project. In the next project, what we did is we tried to see if we change water chemistry, how water quality parameters, say if pH of the water is changed, if we have certain salt concentration, say groundwater versus surface water versus marine water, how that salt concentration will also change the performance of our material. Okay. So with low pH, we see high PFAS removal. With low amount of natural organic matter in the water, we see high performance of the material. With obviously, if we increase the PFAS concentration, the material surface is limited, so we keep losing the performance. So there are multiple different variations we tested, and we kind of try to optimize at which conditions we can use our technique and in which conditions it will not perform well. Currently, we are working on a different process because in the previous one, what we have found is that our technique is good to some degree, but we are seeing partial deep transformation. We are not breaking a lot of carbon fluorine bonds. So what we are doing now, we are taking another material called titanium dioxide, not iron. We are replacing iron with titanium dioxide. And titanium dioxide is a photocatalyst. What it means, if you use them under UV light, that titanium dioxide can react with water molecule and create reactive oxygen species. And then those reactive oxygen species also can react with PFAS and degrade them. So what we are seeing now in case of this is that we see a lot of concentration decrease for PFAS, and we see also fluoride generation, meaning we are breaking the carbon fluorine bond, and the fluorine is generated as fluoride, which is a direct evidence of degradation of PFAS here. Okay, so these are all these experiments we do where we take the nanoparticles as powders form, granular form, like activated carbon. So we are trying to go into a different route because you cannot just use nanoparticle powders when you are trying to apply. And in granular activated carbon, that might be easy, but for nanoparticles are expensive too. That's another side. And we want to make sure that nanoparticles are not getting released in the environment. So we have this project where we are trying to use 3D printing to create macro scale filters. Like, I don't know if I have, no, I don't have the other picture. So these are small filters that could go into this type of tap in front of the tap, where they could take out PFAS from there. So it's not in powder form, but more of a macroscale porous structure form. We call them aerogel, but we can print them and we can dry them to make these aerogels. So the idea is to use the same type of material that we are studying on the other side, like the ideas, like the studies I showed before, but can we actually apply them in a real water treatment system, like not in water treatment system, but point of use at home water treatment systems. This is a new project we just got. We are starting to work on this, that we have our water treatment platform, Nano, and we are collaborating with colleagues at Clarkson University, who has a nanomaterial-based technology that can detect PFAS in very, very low concentration within minutes. Okay, and that is very important because the conventional technology we use, like the liquid chromatography, mass spectroscopy techniques, it takes long time. We have to collect the sample, we have to extract the sample, PFAS from water sample in different ways. But if we can design portable technologies that can detect PFAS in low concentration, that will be useful. So we are trying to connect our treatment technology with their sensing technology. Can we detect and destroy PFAS at the same time? Okay, this is a project we are doing. So yeah, I'm coming back to this. Okay, so those are mostly my work, and we can discuss a little bit more after this. So for Nebraska, I think it's very important to understand how PFAS moves in agricultural and food systems. And for water, agriculture, food, and economy of Nebraska and in the Great Plains, it's going to be very, very important. And that's why we did this, we are taking this Great Plains PFAS initiative where we are bringing in people from across the campus and across the different states. Here, like we did this symposium and workshop in September last year. We brought in UNL, different schools from North Dakota to Texas to organize this workshop where we got perspectives from scientists from EPA, Nebraska Department of Energy and Environment, and other agencies like industries also and utilities partners to come together and talk about what we need to do to understand the problems, extent of problems in Nebraska and in the Great Plains. Anyone heard that Grand Island found PFAS in their water? they're going into class action lawsuit.
I know they have uranium.
Okay, they have everything then. So there, so yeah, so we had like a lot of participation from different people, so we're grateful to have that. And this is my group. We sometimes do have fun. Not always work in the lab. So yeah, with that I'll stop and take any questions. Thank you.
I got a newsletter yesterday from Madison Engineering. And there's someone there is using machine learning or artificial intelligence to help them design the nanomaterials for PFAS. Do you know how that would work and why they would go with that approach?
Yeah, no, this is really like I didn't show that part. We have a project on that too. So the idea is that, like, say, for example, I started my faculty position in 2016. I have been working on graphene and iron for last 9 years, and we are figuring out this is probably not the best material for me. Right? Then we are starting with graphene and titanium. Or we have a funded project, we can go for 3 years or more. So if we keep going on this route, when will we figure out what is going to be important or not? So I think the idea is not to terminate experimental ways, but help the experimental pathway to design the material for treatment. Because if we are looking at, say, there is already a lot of literature on PFAS bonding energies, right? Then we can calculate how much energy or what type of radicals we need to break that bond, and what even happens when we are looking at surface interaction. For example, one of the things we always heard that advanced oxidation, the process we are working on, it should not work. Every single, like my NSF program manager, he said it should not work.
Well,
we see that evidence.
I know that too. You get the OH radical, just if you did a Fenton reaction, it wouldn't work. But on the surface, apparently it's working.
On the surface, it works,
Yeah.
which people, so now I think it's not only machine learning. I don't think only machine learning will help. Machine learning with mechanistic modeling, like molecular simulation, you have to have multi-scale modeling. Like machine learning, we only can do data analysis. That's not going to help overall. But if you can couple with mechanistic modeling, then it will help. So that's what we are trying to do. Like we have colleagues who are working on machine learning, but looking at more physics-based machine learning, and then we are trying to couple molecular simulation. And I don't do any of this, so I need to have colleagues who can do this. Yeah, but yeah, I think probably you are talking about. Yeah, I know who you are talking about in medicine. Any other questions?
How would you determine toxicity, maybe of some of the reaction products and treatment?
I will not do it. I will get somebody to do it. So, I don't think I showed that project. So we have another project where we are putting these nanomaterials on membrane surfaces. And this is a collaboration with Kentucky, University of Kentucky. And so we have a toxicologist in the team who is looking at PFAS toxicity before and after treatment, like taking the influent and effluent of the system and see if we can identify which products are there, plus if she can look at toxicity, then we will know if the degradation products are toxic or non-toxic, right? So
What methods are issued?
so they use nematodes, they use C. elegans, yeah.
So
C. elegans.
bioassays?
Yeah.
Okay.
But I think at this point in PFAS world, it's like whoever has what, they are jumping with that,
Yeah.
so.
Okay.
Anything else?
Also, there are other derivatives of this organic compound,
Yeah, there are thousands of them.
so they are also difficult to isolate them and to filter it out.
Yeah, so if I go very simplistic, the simplistic form is like PFOA and PFOS, these two are the 8 carbon chain, legacy PFAS. It's easy to actually take them out. because they are very hydrophobic. You can take them out with almost any carbon-based material. The problem is with what happened, so PFOS and PFOA were banned and others, like these two are only the banned ones. So what happened after that, companies start to make newer ones, which are shorter chain. The idea was the long chain ones are hydrophobic, so they will be more toxic than the short chains. But now short chain ones are also found to be very toxic. The problem with the conventional technologies is taking out short chain ones because these are more hydrophilic compared to the long chain ones. So it's more difficult to take out the shorter chain. That's where the new technology development should be there. Like, can we target shorter chain PFAS? Or because long chain is not that much of a problem. And over the years, what I learned, you cannot really solve all the PFAS problem with one technology. You need different technology. It may be more as a treatment train, like you have one treatment process to take out long chain ones. After that, the water goes to the next one, and you design a treatment system that will take out the short chain ones. You cannot do all with the same technology. Yes, if you use reverse osmosis, you can do it, but that's going to be very expensive.
You know, the EPA directive, when was it supposed to be in effect?
Oh, this one, so the drinking water one is a law, right?
It's already
Yeah, that is a law. So
compliance wise, when the
compliance wise, by 2027, they're supposed to be in compliance, like every utility should be in compliance.
so you know, last year I was visiting the South Sioux City utility, and they have one well at the end of the runway that was picking up the PFAS. I don't know, because they had a plane crash some years ago, the United plane. I don't know whether that or just a normal. But they are saying that if they go through a treatment, that well pumps 10 million gallons per day. So what to do? What type of treatment? Or abandon the well? That might be the cheaper few, $4 or $5 million they spend for the well. So those are kind of the things how the utilities are going to deal with pump. You know, one place the water is coming at 10 million gallons per day. What treatment is available unless you
Yeah, so I think that's where that's when this is not the research for that kind of work. There we have to look at just what is available right now and do kind of cost benefit analysis and see what can be done. Like some pilot scale work and
or maybe they try first powdered activated carbon or something.
Yeah.
Yeah, so there's big cost for utilities.
yeah.
Rule of thumb, would the shorter chain PFAS be less toxic? Because they're not accumulating in the body? Or not?
I don't think that's the evidence. Like, it's supposed to be less toxic, but I don't think they found it a ground truth yet, like if it's going to be like that. Like,
I just-
they are supposed to be like less accumulative, but they still accumulate. Like, it's not like because they are charged, and then electrostatic attraction plays a role there too. So
Do you know what came up with the 4 parts per trillion MCL?
that's a great question. I don't remember, but I remember that EPA did some initial testing and then they extrapolated that it was not, I think, I don't think it was experimentally validated at 4 parts per trillion.
It's a model.
It's a model.
Yeah, Iris.
What I think is missing is me speaking, is that there's plenty of case studies of chlorinated solvents causing cancer all throughout history. But there is the PFAS causing cancers. You don't hear about it. It's not in the, I mean, the couple articles, but it's not in your face. So
They're in, like, if you follow like North Carolina and Chesapeake Bay, these are the 2 main places where they found direct evidences. So though, like, if you talk with people in North Carolina, they know more.
Yeah.
But I also think, like, overall, this is not just about PFAS, but in general, Like if you think about 30 years back, how information were disseminated, there was probably one TV channel or like few TV channels, and people are looking at one information most of the time. Now there are so much information, so much different information. It's not propagating as much as it should. That's a different concept, but I feel like that has partly to do with.
The entire carpet industry in Alabama, Georgia, I don't know what they're going to do.
Oh, even paper industry too. Yeah. But now like what this administration did, the first act they did. So drinking water regulations is there. Then next came in December the surface water. It was not a regulation, it was the health advisory for surface water for PFOS, PFOA, and 60 FTS, probably 3. And then they were setting up the regulations for industrial wastewater. So that was sent in last June to White House for review and approval. And what happened the first week of this government? Can anyone guess? Yeah, done. That's done.
So is the Scotch Guard still in use
So-
or it's replaced?
I would think so.
So industries don't have to be like compliant because there is no regulation. Yes. Right, there will be lawsuits. There are like every week there are some lawsuits going on. But yeah, if there is no regulations, they don't have to comply.
In one of the treatment method, you mentioned like the thermal,
Sure.
thermal one to remove the PFAS. Like that can also be removed from the water system. Like,
Yeah, yeah, go ahead.
like can that be also be used to remove that PFAS from the water? That thermal one.
Yeah, but thermal in water is very like it's not efficient. It's not going to be efficient. It's going to be like more and more the idea is that you adsorb in on a surface and then if you do thermal treatment of the adsorbent, then you can because these are trace amount. So if you are not concentrating that water, you are losing a lot of water and like it's just inefficient in general. And the heat treatment in water is not as efficient in a solid surface.
Yeah, and their thermal resistivity is very high.
Very high. So
So these treatment plants or technologies, are they made specifically for wastewater treatment plants and maybe domestic water? What about surface water systems like rivers and streams and
So wastewater is taking care of the surface water, right? Because wastewater treatment plant is before, so if we go here. So this is where wastewater treatment plant is, treatment plant to here, this is coming, right? Before the river or the lakes, they're disposing, you have the wastewater treatment.
yeah, I mean for just runoffs.
Oh, runoff. Yeah, that's a good question. There is no really treatment process unless you are doing stormwater treatment using like geomedia or bunch or that type of thing. Like that's a issue with farmlands too, right? So there will be a lot of runoff.
So that precisely the problem in Alabama, Georgia, that the industry, what they do, they spray the water in the forest land. Runoff goes to Alabama rivers.
Thank you.